All right. Well, hello, Honors Algebra 2. This is our first lesson in terms of probability for this unit. 11.6 wrapped up the statistics part, and so we're now going to focus on probability. There will be a little bit of overlap between the two, but this will be kind of a separate kind of almost unit that we're going to be focused on for the last 5 or so lessons. So we're going to start with just our intro section. So this is the intro to probability. Just to get you thinking about probability, I've got this example problem here. So suppose that 4 friends get together to study at Tim's house for the next test in Honors Algebra 2. When they go for a snack in the kitchen, Tim's 3-year-old brother makes a tower using their MacBooks. Unfortunately, none of the students had their names on the back, and they no longer have the stickers. So when they left, each student took one of the MacBooks at random. When the students returned home with their MacBooks, students were surprised that none of the 4 had their own MacBook. How likely is it that one of the 4 students ended up with the correct MacBook? So if you wanted to give a guess at this problem, you can. I will just let you know I'm not going to answer it for you. So if you want to think about it, feel free to do that. By the end of this unit, though, you can probably come up with a pretty good guess as to what that probability should have been. So to start with, let's just go through quick definitions. This should be a pretty short section of the notes, pretty short homework for you too on big ideas. Let's start with just talking about the law of large numbers, what that is. So what the law of large numbers says is that as the number of trials increase, the expected probability will get closer to the experimental probability will get closer to the theoretical probability. And we'll talk more about experimental and theoretical probabilities in a few more sections. So the second thing, interpreting a probability. When you interpret a probability, it is the percentage of successes in a long series of repetitions. So that'll be something we'll practice, and in fact, that'll be our first example we'll look at. All right, third thing, probability notation. So you've got P of X, which again is read as the probability, or P of X denotes the probability of some event X occurring. And we'll talk more about those events, what are called sample spaces, in a later section of the notes. So the first example, the probability of getting a sum of 7 when rolling 2 dice is 1 out of 6. Interpret this probability. So what we would say is that the percentage of 7s that are rolled by 2 dice is about 1 out of 6, or as a decimal, 0.16 repeating in a long series of repetitions. In other words, if you were to roll a pair of dice for a long series of repetitions, and when we say a long series of repetitions, we're talking like 50, 100, 1,000 times, but that the percentage of 7s should be about 16%, or 1 out of every 6. That's not to say that if you roll a pair of dice 6 times, that you're going to get one of those to be a 7. The law of large numbers says that's only true for very large numbers of trials. So 6 would not be a very large number of trials. Really, in fact, 50 and 100 aren't all that large numbers of trials. We're talking like thousands of trials being a large number of trials. Okay, so imagine that you're flipping a coin. Write down the results of 30 imaginary heads, or imaginary flips. So for example, they've got heads, tails, tails, heads, tails. So go ahead and write out what you think would be the results of 30 imaginary flips, and then I'll write one for myself. Okay, so depending on what you came up with, here's what I'm going to write down. That there is a possibility when you are flipping an imaginary coin 30 times that they would all end up being tails. Now, you're probably sitting there thinking, well, that's not very likely, and that's true. It's not very likely. It's much more likely to have about a 50-50 split of heads and tails. But this is just as equally valid a result as any other result you may have written down. So when you think about it, let's look at these 2 examples here. You've got 2 examples, one of which says that they got heads, tails, heads, tails, tails, heads. The other is tails, 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 heads, heads, heads. Which of those do you think is more probable to occur? And if you think about it, the first one, you ended up with 3 heads and 3 tails, which is just what you'd expect if you flipped a coin 6 times. The second, you ended up with 3 heads and 3 tails. So, really, these are equally likely outcomes. They both have the same number of heads and tails. You might have been thinking of the one on the left just because it's a little bit more variable, but that's not necessarily going to be the case. So some myths about randomness is that we kind of have our own expectations, and those are rarely met. So when you're thinking about what you expect to happen, it's usually not going to happen that way. So some of those expectations might be an equally likely outcome when actually one is more or less or just as likely as the other. The other myth about randomness is that really, I mean, we won't get too much down this rabbit hole, but it's very difficult to be truly random. And again, we're not going to get too much into that. If you wanted to do some of your own independent research, there's some different articles you can read about what's called chaos theory, which is some of the theories behind randomness. But obviously that's something for you to do on your own if you'd like to look at. So I did include this little applet. I'll put probably a link on Schoology for you so you can go directly there, but if you wanted to just click on the link that's in the notes, you could do it that way. I've got it pulled up, so some more kind of in-depth look at kind of how this all works. So what this does is it lets you simulate the probability of heads based on the number of tosses, and we're going to keep that probability of heads right at 50%. So let's just do a few tosses and see where that puts us. So maybe let's just do 2 tosses, and in 2 tosses we had no heads. So that would indicate that the probability of heads is 0 and the probability of tails is 100%. Which obviously is not what we would have expected. We would have expected after 2 coin flips to have had 1 heads and 1 tails. So let's maybe increase our number of tosses. So let's toss it 5 more times, see if we get closer to 50%. And we're not even. And if you look at it, we've only got 1 heads when we should have had about 3 or 4 heads. So let's increase our number of tosses again. Let's go 15 more. And so after another 15, so we now tossed it 22 times, we are now up to 8 out of 22, which are heads. So we're now up to 36%. So we're getting closer. Here's what large numbers says, is that if I really crank this up and say toss the coin another 200 times, and it's going to speed through this here, is that the more times I do it, the closer that probability is going to get to that 50% mark that we would expect. So in this case, our experimental probability would be that our percentage of heads, you can see kind of up here, is 0.469, so right around 47%, and tails is around 53%, which as you can see is much closer to the actual value. In fact, if you look at kind of in the long run here, we started off kind of low for our proportion, and we've slowly but surely gotten closer and closer and closer to 50, and you can play around with this on your own if you want to. But the idea is that the longer you do this, the more times you toss that coin, the closer that probability is going to get to 50%. And yeah, at this point, after 422 tosses, we're now at 49% heads and 51% tails. So pretty darn close to that 50% mark that we would have expected. So something kind of cool to play around with. You can even change, if you wanted to, the probability of heads to being less than 50% or more than 50%, and just kind of seeing how that affects the long run value for the true probability. So that being said, that's all I've got for you today, guys. Have a good rest of your day, and I will talk to you next time.